Um, Welcome to lesson 3 of momentum and impulse. So, kulama video adlulile sidiscusse sort of theory sacala ama definitions akhona kuma exam guidelines. So kulama video alandelayo ukusukela kule ngizobe ngidiscussa ama questions, right? So here lapha ngwami question 3 taken from some notes. But a car with a mass of 1,200 kg is traveling at 72 kilometers per hour when the driver sees a dog running across the street. He applies the brakes and 10 seconds later the car is moving at 18 kilometers per hour, right? So we have a car. Okay, so we have a car. Let's say it's moving towards to the right maybe, and then it's moving at 72 kilometers per hour, right? And then the driver sees a dog. Okay, kunenjanyana la somewhere, and then he applies the brakes, and 10 seconds later the car is moving at 18 kilometers per hour. Okay, so question 1 but calculate the initial momentum of the car, right? Take note ukuthi velocity in our case, it's not in SI unit, it's in kilometers per hour. But then masebenza ama calculations wethu, we need velocity to be in meters per second. So first thing that we have to do is to convert those kilometers per hour to meters per second. So okay, so must convert to, we know what 1 meter per second is equals to 3.6 kilometers per hour, right? Sorry, per hour, right? So this implies that 72 kilometers per hour is equals to 20 meters per second, right? So when you say 72 divided by 3.6 uzokuthola ukuthi that's 20 meters per second. Okay, so velocity yethu lapha it's 20 meters per second, right? And then same thing with 18 meters per second after he applies the brakes. So 18 meters per second, so sorry, 18 kilometers per hour is equals to 5 meters per second. So now 18 divided by 3.6 uzokuthola ukuthi that's 5. So therefore 18 kilometers per hour is equals to 5 meters per second. So now we can proceed with our question. We can proceed with question 1. But calculate the initial momentum of the car. So initial momentum of the car is the mass of the car times the initial velocity, right? Where the mass of the car is 1,200 kg times the initial velocity, which is 20 meters per second. Therefore, the initial momentum of the car is 1,200 times 20 will give us 24,000 24,000 kilograms meter per second, right? And then in the direction of the velocity of the car, right? In the direction that the car is moving. Okay, remember momentum is a vector quantity, therefore it has direction, so we have to indicate direction. Okay, so question 2, but calculate the final momentum of the car. So that's PF is equals to the mass of the car times the final velocity. The mass of the car is 1200 kg. The final velocity is 5 meters per second, right? So 1200 times 5 is 1200 times 5, that's 6,000. That's 6,000 kilograms meter per second in the direction of the car, in the direction that the car is moving. Okay, and then question 3, but calculate the change in momentum. So the change in momentum is equals to the final momentum minus the initial momentum. So say scenario is final momentum and we have initial momentum already, so we can go ahead and calculate change in momentum is the final momentum minus the initial momentum. From question 2, the final momentum is 6,000. From question 1, the initial momentum is 24,000, right? So when you say 6,000 minus 24,000, that's minus 18,000. That's minus 18,000 kilograms meters per second. So the change in momentum is 18,000 kilograms meters per second in the opposite direction that the car is moving. Okay, so question 4. Question 4, but calculate the net force applied by the brakes of the car. So khumbule ukuthi Newton's second law of motion in terms of momentum states that the net force applied is equals to the rate of change in momentum. So that is F net is equals to the rate of change in momentum. F net is equals to delta P over delta T. With delta P says naye, that's change in momentum. It's minus 18,000. And then the time is given in the question, that's 10 seconds. So the net force is equals to minus 1,800 newtons. So the force that is applied by the brakes of the car is 1,800 newtons in the opposite direction that the car is moving. So yeah, we are done with this question. So if we go back to our notes, lapha bakhuluma nge-principle of conservation of linear momentum. So masithoma ngama-lesson momentum and impulse, ngachaza ukuthi this principle is very important to most exam questions, especially na involve ama collisions. So you'll have objects colliding and then you'll calculate the total linear momentum before collision and the total linear momentum after collision using this principle AT. The total principle of conservation of linear momentum AT. The total linear momentum of an isolated system remains constant in magnitude and direction, right? An isolated system or a closed system is a system in which the net external force acting on the system is zero. So a closed system or an isolated system, it's a system where there are no external forces. Because there's no friction and there's no air resistance or any other external forces, right? So this principle of conservation of linear momentum, it applies mostly when we are dealing with collisions, right? So there are a number of possible types of collision that can take place between two objects moving along the same line, that is in one dimension. For example, one moving object collides with a stationary object. The example yalokhu would be when a ball is bouncing against the wall. The wall is a stationary object and Ebola is a moving object, right? One moving object collides with a stationary object. Okay, another collision. Okay, two objects move towards each other and collide. So if maybe you have two cars moving towards each other and then zichayisa. Okay, two objects move in the same direction and collide. Example yalokhu, maybe you have two cars moving in the same direction. Ikoloyi wani ilandela enye, le enye ichayisa enye ngemuva. That is two objects moving in the same direction and collide, right? One unit, okay, another type of collision is when one unit separates into parts. For example, an exploding bomb. One unit separates into parts, an explosion. Even nawucabanga isibhamu nebullet, that is one unit, and then after you pull the trigger, ibullet liyaphuma, and then that is an explosion, right? Okay, and then they tell us the possible results from collisions. So if a collision happens, both objects can collide and stop, right? If inkoloyi zichayisana, singachayisana bese zijame zoyi-2, right? Another possible result is one object moves and the other object stops moving. So in this case, maybe unetracker nekoloyi ziyachayisana, so kenzeka ukuthi nazichayisana itracker lijame still, and then ikoloyi imove to the opposite direction. That is, one object moves and the other object stops moving, right? Okay, another possible result is both objects move but both objects move but not joined. Okay, so in this case, ziyachayisana inkoloyi and then both of them move in separate directions. Another result is two objects join together and move off the same speed. So example a common from exam questions, it's when maybe you have a block and a bullet, right? The bullet is moving towards the block, and then after they collide, they move together in the same speed. So after bullet lidubula iblock, ibullet lingena ngaphakathi kweblock and they move together in the same speed. So those are the results from collisions. So mawenza ama questions related to the principle of conservation of linear momentum. Funda ama-questions lawo carefully analyze ukuthi what happens after collision and what is happening before collision. So also use your logic, apply common sense. So yeah, lokho kuzokusiza ukuthi uphendule ama-question lawo ngcono, right? Okay, so siyachubeka. Here they are talking about elastic and inelastic collision. So sichazile ukuthi in elastic collision the total kinetic energy is conserved. In an elastic collision the total kinetic energy and total linear momentum are both conserved, right? So they talk about total kinetic energy, right? Total kinetic energy and total linear momentum. They talk about total kinetic energy and total linear momentum. So in an elastic collision, total kinetic energy and linear momentum are conserved, right? So lokhu kuchaza ukuthi in an elastic collision, before collision in an elastic collision, both the total kinetic energy and total linear momentum are conserved. So in an elastic collision, the total kinetic energy before collision is equals to the total kinetic energy after collision, and also the total linear momentum before collision is equals to the total linear momentum after collision. In an elastic collision, both kinetic energy and linear momentum are conserved, right? In an inelastic collision, total linear momentum is conserved, right? Total linear momentum is conserved, right? Total linear momentum is conserved, but not total kinetic energy. So in an inelastic collision, so linear momentum is conserved in both cases. If in an elastic collision or an inelastic collision, linear momentum is conserved there, but then the same does not apply for total kinetic energy. Kinetic energy is only conserved if the collision is elastic, right? So the conservation of kinetic energy is determined by calculating the total kinetic energy of all parts of the closed system before the collision and then comparing that to the total kinetic energy of all parts of the closed system after the collision. So nabakhuluma nge-principle of conservation of linear momentum nama elastic and inelastic collision, consider the situation before collision and after collision, right? Okay, yeah, so before collision and after collision, if total linear momentum is conserved, the total linear momentum before collision is equals to the total linear momentum after collision. If total kinetic energy is conserved, the same applies. The total kinetic energy before collision is equals to the total kinetic energy after collision. Ukhumbule ngithe kinetic energy is the energy due to an object's motion. Kinetic energy has to do a moving object, or is an energy that an object possesses due to its motion. Okay, so yeah, let us look at more questions or more examples. Okay, so let us look at this question, right? Lana bathi A 35 kg girl is standing near and to the left of a 43 kg boy on the frictionless surface of a frozen pond. So we have a girl, right? Okay, we have a girl. She's standing near and to the left of a 43 kg guy, boy, right? She's 35 kg. This one is 43 kg, right? They're standing on a frictionless surface. The boy throws a 0.75 kg ice ball to the girl with a horizontal speed of 6.2 meters per second. So this guy throws a ball towards the girl at 6.2 meters per second, right? This ball is 0.75 kg. Okay. So but what are the velocities of the boy and the girl immediately after the girl catches the ice ball? So here we can apply the principle of conservation of linear momentum because we have a closed system, right? How do we know that we have a closed system? They tell us they are standing on a frictionless surface. So there is no friction, meaning there's no external force here. So if there's no external force, we have a closed system, right? Remember, sitifine ukuthi a closed system is a system in which the net external force is zero. That means there's no friction, no air resistance, or any other external force. So again, in principle of conservation of momentum, it is the total linear momentum of a closed system is conserved. Because we have a closed system, we can apply the principle of conservation of linear momentum. So let us apply that principle in this situation. What are the velocities of the boy and the girl immediately after the girl catches the ice ball? So lana sinama collisions I2, right? So first case, the boy, okay, so kule situation here, the boy, it's sort of like an explosion because the boy is holding a ball and then he's throwing the ball towards the girl, so that is sort of like an explosion, right? And then good situation here, girl, it's a collision. The girl, as she catches the ball, it's sort of like a collision, right? So let us go ahead and apply the principle of conservation of linear momentum. So ngizoba nama situation ayi-2, situation ye boy sithome ngayo, right? Ngizothi let the direction to the right be positive. Okay, so the total linear momentum, I'm applying the principle of conservation of linear momentum. The total linear momentum before collision is equals to the total linear momentum after collision. Excuse my handwriting there. Okay, so before collision the boy is stationary, right? Before the boy throws the ball towards the girl, he is stationary, right? So also okay, so before collision we have the mass of the boy and his initial velocity. Okay, wait. Okay, So before collision, in the situation of the buoy, before collision, right, or before explosion, because it's sort of like an explosion. So the buoy is holding ibhola esandleni sakhe. So therefore the buoy and the ball are sort of like a one thing, right? So then before we will add the mass of the buoy with capital B and the mass of the ball with small b, right? And then because they are sort of like a one thing, they are a one system, right? And then they have an initial velocity there, an initial velocity, right? And then after collision, now ibhola na the buoy bayahlukana. The buoy throws the ball away, and then they are separated. So the mass of the buoy times the final velocity of the buoy, right, plus the mass of the ball times the final velocity of the ball. Okay, lapha ngithi u-b ish ngazi ngibhala njani le. Okay, ngizothi v1 vf1 vf1 vf2, right? So that's the mass of the buoy, the mass of the ball, the velocity of the buoy after collision, the velocity of the ball after collision. So before collision, the buoy is stationary and the ball is not moving. So the velocity, the initial velocity there is 0. So this side is 0, right? And then after collision, so after collision, the mass of the buoy is 43 kg. The final velocity, as yes, it's what we want to calculate, right? And then after collision, the mass of the ball is 0.75 kg times the final velocity of the ball. So the final velocity of the ball is minus, because it's throwing the ball to the left, it's minus 6.2 meters per second. Okay, so left hand side we still have 0, this side we have 43 vf1 minus 0.75 times 6.2 times negative 6.2, that's negative 4.875. Okay, so now we can solve for the final velocity of the buoy. So vf1 is equals to 43 divided by 4.875, which is equals to oops, whoa, no, it's a mistake, Lana, it's the other way around. So it's 4.875 divided by 43, 4.875 divided by 43. Okay, so 4.875 divided by 43, it's let me double check my calculations. 0.75 times 6.2. So this is 4.65, sorry, not 4.875. Right. So 0.75 times 6.2, it's 4.65, right? And then the final velocity of the boy is 4.65 divided by 43. So 4.65 divided by 43, it's 0.108 meters per second to the right. Okay, so the velocity of the boy, the velocity of the boy after the girl catches the ball is 0.108 to the right. So ngizoyibhala lana, the velocity of the ball is 0.108 meters per second to the right. Okay. Now we move to calculating the velocity of the girl. Okay, so now to the situation of the girl. So before collision, still we are applying the principle of conservation of linear momentum, which states that the total linear momentum before is equals to the total linear momentum after, right? So before collision, the girl is stationary, right? The girl is stationary, and then the ball is moving towards the girl, right? So we have the mass of the girl, right, times the velocity of the girl, the initial velocity of the girl before collision, plus okay, so velocity of the girl ngizoyibekela istar phezulu ne, just that ukuthi singabi confused. and then the total linear momentum before collision is the momentum of the girl, and then the momentum of the ball. The ball is the mass of the ball times the initial velocity of the ball, and then the total linear momentum after collision. So after collision, the girl and the ball are one system, because lana bayasho ukuthi after the girl catches the ball, right? So when she catches the ball, the girl and the ball become one system now. So we'll have the mass of the girl plus the mass of the ball times the final velocity, right? After collision, now they are one system. Okay, so before collision, the girl is stationary, right? The girl is stationary and the ball is moving. Okay, so the initial velocity of the girl is 0, which means the initial momentum of the girl is 0, right? And then before collision, the mass of the ball is still 0.75 kg, and then the ball is moving to the left towards the girl, at a speed of 6.2 meters per second, right? So it's gonna be 6.2. Oops. Okay, I think pale kuhle lana. Okay, so there the initial velocity of the girl is 0, so the initial momentum will be 0. The mass of the ball is still 0.75. The initial velocity is 6.2 meters per second, negative 6.2 because it's moving to the left towards the girl. And then after they collide, the mass of the girl is 35 plus the mass of the ball is still 0.75, right? And then the final velocity of the girl and the ball is this one, which is what we want to calculate. So the final velocity now will be 0.75 times 6.2, and that is 4.65, right? So here, negative 4.65 divided by 35.75. So this is equals to negative this is equals to negative 0.13, right? 0.13 meters per second. Okay, so therefore the velocity of the girl is 0.13 meters per second to the left. Okay, to the left. Yeah, so that is how we calculate it. So this one is sort of like two scenarios. The first scenario, it's an explosion between the ball and the boy. The second scenario is a collision between the girl and the ball right? So first scenario, the girl, the ball and the boy are one system, and then they, as the ball throws away the ball, it's an explosion. They are separated now, right? And then second scenario, it's a collision between the girl and the ball, right? The girl is stationary, and then the ball is moving towards the girl. And then after they collide, the girl catches the ball, and then because they are standing on a frictionless surface, as the girl catches the boy, she moves at a speed of 0.13 meters per second to the left. Okay, I hope this question makes sense and how I've explained it. If you are confused, send me a text there on WhatsApp. Ungitshele ukuthi ulahleka kuphi, yini ongayizwisisi. Ngizame ukuthi ngikuchazele kuhle. Okay, so ama scenarios esinawo ukhumbule sithe we have these scenarios, right? So kule question ebesiphendula singasho ukuthi scenario number 1 is an explosion, right? One unit separates into parts, an explosion. So one unit lapha, it's when the boy is holding the ball in his hand, and then when they separate, that's when he throws the ball away towards the girl, right? So that is an explosion. So that's scenario 1. Scenario 2, it's when it's one object moving collides with a stationary one. One object moving in our case, it's in scenario 2, it's when the ball moves towards the girl. The girl is stationary, she's not moving, but then the ball is moving towards the girl, and then they collide. And then the results, scenario 1, it's an explosion. Both objects, they move, but then are not joined, right? So the ball and the boy move in opposite directions. Scenario 2, two objects join together and move at one speed. This is the girl catching the ball and then move at one speed. Okay, I hope it makes sense. If it still confuses you, ungitshele lapho ku WhatsApp, ngichazele kuhle. Right, so yeah, I think that's enough for this lesson. Sizochubeka throughout the week, spendule some more questions ku momentum and impulse. So the best way to understand this chapter is to practice as many questions as you can, and then now we'll apply common sense yakho as you answer these questions. Now apply common sense yakho kuba easier ukuthi uzwisise ukuthi kwenzakalani. So if you are given a question like this one, right? So it's best ukuthi nawe uzidrawele inthombe, sort of uzama analyze the situation ukuthi kwenzekani kuhle kuhle, yabo. So try to visualize the scenario, try to visualize, so ukuthi ukhona understand kuhle na ubone ukuthi okay, nase ngiphendula le question ngizoyi approach kanjani. So uyabona mina it was blank, so ngazidrawela i scenario, but okay, but the 85 kg girl is standing near to the left of a 43 kg boy on a frictionless surface. So ngiyambhala that 35 kg girl, she's standing to the left of this 43 kg boy on a frictionless surface, right? Ngizama ukuvisualize leyo situation, okay? And then bathi the boy throws a 0.75 kg ice ball to the girl with a horizontal speed of 6.2 meters per second. But this boy throws a ball in a horizontal direction to the girl, right, at a speed of 0.62 meters per second at this speed. So nahi bolo leyo ngiyithrowa lapho. Okay, this guy is throwing this ball towards the girl, and that ball is moving at this speed. Okay, so ngizama ukuvisualize this whole situation, so kuba easier mase ngiphendula ukuthi okay, this is the scenario, kwenzeka sona so I'm applying my logic, kuba easier ukuthi ngi-understand ukuthi kwenzakani, right? So ngi-encourage na ukuthi wenze the same. I-question nabakunikele yona, try to visualize the whole scenario, udraw inthombe when necessary, analyze the situation, apply your common sense, yeah. And then ama-question e-physics vele afuna uwa-approach njalo, laba testa i-understanding yakho nokuthi ucabanga njani. Draw inthombe man ukuthi zikusize ukuthi uzwisise, yeah, into engayitsho ngileyo. So yeah, if this question yaconfuse, let me know lapho ku WhatsApp, ngizozama ukuthi ngikuchazele yona ukuthi kwenzakalani kuhle kuhle. So yeah, sizochubeka nokwenza ama-examples some more, because the only way yokuzwisisa this whole chapter is by doing examples. And then enye into ozoyinotice ukuthi ngiyazama ukuthi okay, nasithoma this lesson senze ama-definitions, right? And then as I answer lama question, ama principles lawo esiwadefinile ngiyawa-apply somehow. yabona, in this case la, I'm applying the principle of conservation of linear momentum. You should be able to define that principle, and then you should also be able to apply it. Don't just understand the definition, be able to apply the definition. That's how physics ungayimastera ngakhona. Understand the principle, know how to apply it, right? So yeah, I think that's it for this lesson. Yeah, until the next one.